Hello everyone, welcome to our presentation. My name is Arpad Forberger and I'm one of the application engineers here at the company. And today we are going to talk about and take a look at battery design in COMSOL Multiphysics. So here's the agenda for today. What you can see here is a battery pack, and we want to investigate the temperature distribution of that one. So how the temperature difference will behave the performance. So that's our main goal, how to do this in COMSOL Multiphysics. And we will also show up some further steps, how you can extend the model to investigate like thermal runaway and co-simulation with that one, and how you can find further resources here. So a few words about COMSOL Multiphysics. So what is it about? As the name says, it's for multiphysics problems. You can start with a single physics like heat transfer, structure mechanics, fluid domain simulation, and you can couple them to a real-world scenario like our battery here. So here in our battery model, there are several different physics like chemical reactions, thermal distribution of the pack, and so on. So that's where we can pack up everything in a one single user interface. So that's where COMSOL is a great tool to add. So this is the current product suite. So all the modules are grouped together into four big pictures to four big physical domains. And what we are looking into is the battery design module and all the features and capabilities of that one. So we will investigate those scenarios here. And why do modeling? So why this modeling stuff is all about? So well, you want to investigate the performance of the packs. You want to create know-how of the battery pack, but you don't want to do such labor work, such laboratory tests. You want to reduce the time to market, and you don't want to investigate that much physical properties and physical prototypes. So that's where you can build up virtual prototypes, and you can do this in a simulation environment like here in COMSOL Multiphysics. And you can also do out-of-range simulations that may not be possible with physical prototypes, and you can create optimizations like the maximum load that the battery pack can bear, and other optimization algorithms can be attached to your model. So what kind of battery models are available in COMSOL Multiphysics? Let's see, if you are a researcher, you want to do some research, like fundamental research of the chemical reactions in the packs, then that's the right to place here your microtopography data. You can import it into COMSOL, and you can create a very detailed heterogeneous model like here at the very top of the slide. Then if you don't need that much of a detail complexity, and you are rather a designer than a researcher, then you can go for lumped parameter models, and you can use these Newman models like here, if you want to investigate a cell rather than the heterogeneous topography of the battery itself. So COMSOL supports various components from 0D to 3D models, and if you want, you can further reduce the model complexity with these lumped parameter models. So that's how you can support your battery designs with COMSOL Multiphysics. So that's all available depending on your position, whether you are a designer or a researcher or somewhere between. This is the physics interface for the battery design module. And as I mentioned earlier, there are several different physical phenomena that occur here. And everything is supported here within one module. You don't need any additional module to do that. So it supports all the chemical reactions, like you can see here on the right-hand side, electrochemistry parts, the battery interfaces with the built-in lumped interfaces, and also all the heat and fluid domain calculations. So you can investigate further with these virtual prototypes. And let's jump into our lithium-ion battery model here. So this is the model that we want to investigate here. And you can see this is a 6s2p configuration. There are solid and fluid domains. And we want to investigate what will be the temperature difference between the cells. And we will use a lamped battery interface here and set up the corresponding boundary conditions. And we can investigate the scenarios much faster without building the physical prototypes. And of course, later we can extend the features and the capabilities. So here, let's take a look how the model looks like and what kind of boundary conditions can be applied and how we can set up this in COMSOL Multiphysics. So everything here is parameterized, the geometry, the boundary conditions. So if you go to any of the parameter settings, literally wherever you can click, that can be a parameter like some of the geometry parameters here in COMSOL. So that's super easy to do that. You can use the units in the brackets. Then there is a separate list for the battery parameters like the capacity of the cells, the different conduction and heat transfer parameters, and some reference values to add for later references. Then we can investigate further the material settings, and we can add the custom coordinate systems. So if we go further down, then you can add the analytic functions here, or you can import measurements. So if you have some measured data like the open cell voltage, that can be imported, and you can compare that with the simulation results. And since we have a cylindrical design, it's easier to add parameters in a cylindrical coordinate system. So that's where you can add your custom coordinate system. Then going further to the materials, so we have an air domain and all the surrounding materials are defined here. And we have some solid domains that are defined as aluminum here. So this is the battery section for the materials. And then going further with the physics setup. So we have a heat transfer and fluids interface, separate physics for the fluid domain and for the solid domain. So here the surrounding fluid is air. You can see with the selections, and if we apply a cut plane here, we can look into the model quite easily. So we can see what's inside the physical domain. And then we can add the heat flux, so how the temperature will transfer to the surrounding, to the environment, and all the surrounding boundaries are using a constant heat transfer coefficient here. But if you want, you can add the forced or natural convection. So there are closed form solutions for calculating that coefficient. So you can use that one as well here. So that's for the heat transfer part. And for the solid domains, so we have 3 cylinders, three cylindrical domains, and the transfer coefficient is applied as a diagonal form because of the cylindrical physical properties. We have different values for different coordinate directions. So that's why we defined earlier our custom coordinate systems at the top. So we have the same settings for the 3 cylinders, the same settings are applied here, and then we have some convection and conduction for the solid parts. So that's all for the heat transfer part, and now we can go to the lumped battery interfaces. At the equation view, you can always check you are really at the right equation, you are really solving for the right equation, so you can check whether you are at the right place. And then after that, we can switch the operation mode. For this simulation, it's galvanostatic, but we can switch to charge and discharge cycling. So that will be the extension of this model here. The current is a parameter, so you can create parametric sweeps quite easily here. And there are some additional setups for the batteries. So we have some data from measurement. We can easily import it into COMSOL Multiphysics, and we can use that in the setup for the open cell voltage. And for calculating the losses, there are various options. So you can set up like here for ohmic and other activation over potentials. There is a huge list of losses that can be taken into account. So all of those parameters, and you can investigate how they affect the aging and the performance of the battery pack. So we have 3 of these lamped battery interfaces, 3 identical cylindrical batteries, and that's the physical setup. And since we have more than one physics interface, so we have a coupled physical solution here. So we couple the lumped battery interface into the heat transfer in solids and fluids interfaces. And that's how you can create with a one-click coupled multiphysics simulation in COMSOL Multiphysics. So here you can see 3 lines for the 3 temperature in the 3 battery packs, and you can see there is a slight difference between the packs. And here you can see the cell voltage, how it drops during the simulation. So you start with an initial value of the voltage, and it starts to drop as you charge it, discharge it. And here you can see the final result for the temperature distribution. And yes, the packs in the middle, they are roughly 2 degrees of Celsius hotter than those that are on the outer perimeter of the pack. And for that, we can extend the model. So we switch from galvanostatic operational mode to charge and discharge cycle. And we can set up additional simulations to investigate how the battery will age, how it will fade during ages. And we can calculate it for years. So yes, we switch to charge-discharge cycling mode. So that's another operational mode. And again, all the physical properties and additional parameters are set up here. We have very wide, detailed description of how these losses can be modeled, and everything is set up using the parameter list. So you can run parametric sweeps to investigate which parameter has the highest impact of the cell's performance. And if we go into the study, so we have a so-called parametric sweep. So here we sweep the initial voltage and also the state of charge to see what will be the effect of these parameters on the aging of our batteries. And the simulation here runs for 2 years, and we can investigate how our batteries will lose capacity and will fade and degrade over years. And there is a 1-cycle simulation also. So here you can see curves. So on the vertical axis, the cell health, which is 1 at T0, and they will degrade as we charge and discharge our batteries. And if we use different initial state of charges, you get different curves. So if you have higher initial state of charge, your battery will fade faster. And here you can see the potential and the current, how it changes over time during these charge and discharge cycles. And we can also see the voltage change and the state of charge during 1 cycle here. So that will be our 3rd plot that will be plotted here. Yes, this is it. So here on the vertical axis, the voltage, on the right-hand side, and it's the current for 1 cycle. So you can investigate these effects without creating labor work, without doing laboratory measurements, and you can investigate the parameters effect much faster than with these virtual prototypes than with physical prototypes. So that's one key advantage here with these digital twin models here. So that's our battery model. To wrap up our results here, you can see the temperature distribution again here. As again, the inner batteries will get higher temperatures, roughly at 2 degrees of Celsius, and then you can mirror and duplicate it, so you can build much larger battery packs, and you can investigate how the temperature will rise and how the temperature will change with this one. Some further steps on how we could extend the model. So if you want to create a battery management system, or you already have that one, and now you have a wide complexity and high complexity battery model, then you can export your finite element model into a co-simulation manner. And that place you can create a BMS also, so you can investigate these effects here. You can also model thermal runaway. So what happens if one of the cells in the pack goes out and increases the temperature? And also you can add active cooling, whether you are not aware that passive cooling is enough or good enough, then you can switch to model an active cooling here. So that's also possible with further resources. Thank you for joining, and I hope you learned something new. And now we are ready for the Q&A.
That was Battery Design with COMSOL Multiphysics by Arpad Forberger. Arpad is right here with me in the studio, and if you have any questions to him, put them in the chat window on the right side of your screen. Hi Arpad.
Hi Angelika.
Welcome.
Hi, nice to see you.
This was a really nice session, thank you.
Thank you.
So, Previously, I asked in the chat how many conferences people attended. Guess, what was the biggest number?
Maybe a few, maybe less than 10, maybe.
20 plus was the biggest.
Wow, wow.
I know,
That's amazing.
right? That's
yeah,
like
absolutely.
a lot.
Yeah, that's a lot.
How many sessions did you attend since the beginning of 2020?
Beginning of 2020, just a few, less than 20, certainly. Yeah, but I try to find more and more. Yeah, thanks to this pandemic situation, there are more online. Yeah.
But is it like in general hard to find like engineering conference which is really interested, or it's there? How many are there? In your opinion, which is good? You know?
Good. Yeah. There are a few, but you need to look into the right direction, and you can find. It's not that easy, but there are some certain points where you can find these nice conferences online. And since they are online, you can go wherever you want. Yeah, you don't need to travel.
And I mean, and you've been in the field for how long?
Maybe 2 decades. Yeah, I started at 2002. Yeah.
It's exactly 20 years. 2002,
oh yeah, so that's an anniversary. Yeah.
Congratulations.
Oh, thank you.
And how long have you been working with the COMSOL?
Maybe 10, 15 years.
10, 15 years. So, what is it that you like about COMSOL?
Well, that's typically for multiphysics problems. That's what I really like, and certainly I have a project right now, and I need to combine different physics, and that's the right place to do. So, different fields, magnetic phenomena with acoustics and stuff like that, structural fields, structural deformations, and you can do everything in one single environment. That's the right place, and it's really easy to use. Yeah.
Is it easy?
Yeah, after a certain point, yeah, we can say, yeah, I know, I get the point. Yeah, that should be easy.
But I mean, how many years would it generally take for a user to go from absolute beginner to a confident user?
Confident, yeah, maybe in months, or rather in
months,
in years, yeah, a few years. But there are lots of online resources, trainings, and yeah, it's the first part is quite steep, but then you can get a very nice level.
So it's like snowboarding, because there is skiing and snowboarding. Skiing easy to start, but then harder, and snowboarding hard to start, but then it's easy. It's like
it's snowboarding. Yeah, it's rather snowboarding. Yeah.
That's very interesting. So actually, we already have a few questions for you in the chat. Yeah. So are you ready?
Yeah. Let's start.
Okay. So first one: have you compared the COMSOL Plus Simulink model behavior with actual physical battery?
I think they think about the results, maybe that is it accurate? I think that's the question about. So you can import, yes, of course, you have measurements. It's for battery for any fields, and you can import that to COMSOL, and you can compare directly with the numerical results. So yes, and then you can iterate on the model to get the right and very accurate model. So so you can always do that, and that's what we always do with finite element modeling. So that's the reference, the solution, I mean, from the measurements, and then you can iterate on the model to get very accurate model.
Okay.
And it's quite accurate, yeah, absolutely. I
think it was clear enough, but let's go to the next question. Is it possible to simulate short circuits? Yeah.
To include in the model? I think that's the question about.
Yeah.
Yes, you can model circuits also, and shortages, absolutely.
Then, hi, I'm a little bit concerned about simulation speed, simulation time. What is a typical simulation time for lumped models? Yeah.
Oh, I see. So yeah, the speed is always a question for modeling and how fast the model runs. So for lumped models, it's in minutes or maximum a few hours of running. And that's a typical simulation time for these models. So it's not that slow, but it's quite fast. I think we can say that.
Okay.
So it's in minutes.
There is another question coming in about short circuit.
Yeah.
But the person is still typing, so let's give him a second. Okay. He was asking about battery short circuit phenomenon. Is it possible to simulate it?
Oh yeah, and there is a built-in model for that in the application library, so we can share the link with the attendee. Yeah, and that's also possible. Yeah, so most of the models that you can find in the library, they come from customers, from real-world problems. So most of them not made of problems, academic problems. So they come from our customers, from our users, from the industry, and from academia as well, of course.
So it's solution which was tried, used, and
Yes,
didn't
and
work.
it can be made public, absolutely. Yeah, yeah.
Okay,
Yeah.
great. Is it possible to calculate mechanical stresses?
Yeah, for stresses, yeah, that's quite common nowadays that you want to calculate those because they can be, the specs can be part of the structure, of course. And since it's a multiphysics solution, yes, you can couple, and we can investigate that in the afternoon's workshop. So there will be an example about that one. So that's the right place to visit our workshop afternoon.
Let me remind you that we have workshops running in the second part of the day. One of those will be run, actually two of those will be run by Arpad, one about battery design and another one about acoustics.
Yeah, that's
exactly.
Right. Exactly.
So you still can register. Just go on Science Engineering website, check out, and join Arpad's workshop.
Yeah, absolutely.
We have still a few questions for you, but we're running a little bit out of time, so we will collect them and send it to you later on, so you can let our audience know the answers. But thank you so much for being here today.
No, thank you. Yeah,
taking your
it was
time.
really fun. Yeah, absolutely. Thank you.
Great.